Are there any questions from the previous class? Audible at the back? Okay, so we'll start with a quick refresher of what we did previously, and then we'll go ahead and talk about some new topics. So we started off with the base rule for ML, and I said that this is probably the slide you'll see in every lecture of this course, and I'm again repeating it. We have the posterior, which is shown on the left hand side, which is found as multiplication of the likelihood and the prior divided by the evidence term, and the evidence term can be found out by either integrating or some summation of the numerator. Can you turn off the fan? I think after 2 to 3 minutes people will come in. And we discussed this problem of predicting the hostel energy consumption, assuming we have a linear model. So let me ask this question now. If you had to predict the energy consumption of this hostel, how would you do that? One, if you had no data, what would you then do? You'd use the prior. So this is the goal. We want to be able to predict the energy consumption like this, where we have a certain mean prediction and a certain sigma in the prediction. But if we have no data previously, we'll have to use the prior. We could choose a prior something like a uniform. We have two parameters, theta naught, theta 1. So therefore the prior will also be in 2 dimensions. Let's say we took a 2-dimensional uniform distribution. We can get some samples from this, and then we can look at the total ranges of the predictions that we can get. This is known as the prior predictive distribution. So the predictive distribution you're getting using the prior, but this is not looking at the data. And we said that what we have just done is, when we are trying to compute this prior predictive distribution, we are trying to solve an integration. Many times this integration is very hard to solve. So therefore we can convert this to a sampling procedure. We then said that let's assume that, so the best estimate for theta naught, theta 1 without any data is just use the prior. But then if we had access to data, we could then check, let's say if we had 3 options, theta A, theta B, theta C, we would perhaps say that theta B is the best because that is most consistent with our data. So what we are trying to find out is the set of parameters which give us the maximum probability of observing this data set. So P of D given theta is what we are trying to maximize. So best explains the data, or which maximizes the likelihood function, where the likelihood is the P of D given theta. So today we'll dive deeper into what the likelihood is. We can get theta MLE, which is the argmax of the likelihood term, and this we said is the same as argmin of loss of theta, where for the case of linear regression this loss function is just the squared loss function. So now we have 2 different estimates for theta naught, theta 1. One, without any data, use the prior. Second, using only the data and no prior, you get the theta MLE. Importantly, theta MLE is a point estimate, whereas the prior was a distribution. But if we had very limited data for some hostel, and if we were to fit a line to it or just do MLE for it, we may get some parameters which may not sound very reasonable. Here it shows that the number of occupants is inversely related to the energy consumption. Therefore, theta MLE is limited. We'll have to be careful about using theta MLE. So what we said is that let's consider both the prior as well as the data, which means that we want to then maximize the posterior term, which is P of theta given D, or find out the theta which maximizes this term. We can write this posterior term as the product of the likelihood times prior divided by the integration of the numerator. For the purposes of this class and in general, we can just consider the denominator to be a constant. It's a very hard constant to evaluate, but it's a constant. So the theta which maximizes the numerator is also the theta which is going to maximize the overall expression. So therefore we can say that we want to find out a theta max, a map which maximizes the likelihood times the prior. So now this gives us the third kind of estimate, which is theta map, but theta map is also at this point only a point estimate. What we'd rather want is something like this, which means that we don't want to just compute theta map, we want to compute the whole posterior, the whole of P of theta given D. And in many cases we discussed that the main challenge is obtaining the denominator term, which is a constant but very hard to evaluate, which is a normalization constant. So therefore there are various approximation techniques for solving this. Okay, we stopped at this point in the previous class. Any questions on this? Okay, if not, let's go ahead with today's class. So we will be discussing the following topics today. We have already done a revision of prior, posterior, MLE and map. We will be looking at distributions, not a lot of them, just a few of them to illustrate the concept. We will be revising the IID assumption, which we have studied in the previous course and a lot of the other previous courses also, but we will take a programming approach to understand it. We will do a much deeper dive into what MLE is, maximum likelihood estimate, and then we will do some derivations for univariate normal data. So I'll directly go to the notebook to discuss distributions. So I'll start off with this, with the normal distribution, and this is what I had also discussed previously. Is the screen visible? Can you see the text at the back? Right. So we discussed that we can create a normal distribution object by calling torch distributions, or equivalent if you want to use something like TensorFlow probability, you could use something similar. So we create a distribution object whose we can define, whose we can figure out things like the support. So for the normal distribution, the support is the whole real line, because you can get parameters, you can get samples from it anywhere on the real line. The first thing we want to be able to do is to plot the probability density function. Right? I hope everyone remembers the basic form of the probability distribution density function. There is some constant, and then there is an exponential term which has a square term in it. Right? So if we were to take length space between -5 and 5, so this is creating an array of 500 numbers between -5 and 5. You are taking the normal distribution, you are evaluating the log probability at each of the x's. So this is a vectorized code, and then you're taking an exponentiation of that. Why we are doing in this way is so let me ask that. In fact, the torch library distributions does not directly give you normal dot prob of x's. NumPy did, but torch doesn't. Why do you think that's the case? If you have to get the PDF, the probability, you have to take the log probability and exponentiate it. Why would they have made such a design decision? Yes, Gaurav. Yes. Yes. So we'll just see this in 2 minutes, why choosing log prob is a better function than to give prob. Right. So, but you're getting the y's, then you're just plotting the x's and y's, and then you can get this kind of a distribution. So this was a distribution centered at mean 0 and variance or standard deviation was 1. Right? But instead, if you had taken a different distribution, or rather the same distribution, but instead of plotting the PDF from -5 to 5, you are now plotting the PDF from -50 to 50. Right? And let's say if we plot this, what can you observe? So previously we were plotting from -5 to 5. Now the same thing we're doing, but the range is from -50 to 50. The standard deviation is actually the same. You've just expanded the x-axis. So can you see that beyond a certain range, the numbers seem to be 0, right? The PDF seems to be 0. But is that the case? Why does that happen? Why do we see that the PDF appears to be 0 for larger, so for values which are away from the mean? Okay, Utkarsh? Okay, so this is a limitation of the way floating numbers are stored in the computer. But mathematically, if you had infinite precision, if you were to write this on a pen and paper, you will not get 0. Right? You will get something very close to 0, but not 0. So therefore, the libraries instead suggest that you plot the log probability. Right? Instead of plotting the probability or the PDF, you plot the log of the PDF. So how do you think they'll calculate this log of PDF? Do they calculate PDF and then do the log of it? No, That doesn't serve the purpose. So you can take the, and this is a good exercise you can actually see. So if we just go to Wikipedia and normal distribution wiki, we can look at the PDF, right? So this is the PDF. You can directly take the log of this term, right? And then you'll get some terms in terms of this constant, and some of the log and exponentiation will get cancelled out in the sense, and it will give you something easier to work with, right? So this is in general a good exercise. You can pick up any distribution, and you'll get a lot of information directly from the Wikipedia page, which contains things like the support, PDF, CDF, mean, mode, variance, etc. You don't need to really go into any other resource if you want to learn about a new distribution. So what we're now plotting is the log PDF for the same ranges of x. And now if you see, the values go till the values become negative. They go till minus 1200, right? But they are not, but you can still see a difference between 0 and minus 20 and minus 40, right? Whereas when you were just plotting the PDF, minus 20, the PDF at minus 20 seems to be the same as PDF at minus 40, right? If you want to just doubly verify this, so let's just do normal dot log prob of minus 20. So if we are looking at the log prob of minus 20 versus minus 40, these two numbers are vastly different. But if instead you were looking at the actual PDFs, both of them are exactly 0, right? Due to the limitation of the floating point representation for these numbers. So therefore, wherever possible, we should just be playing or using log probabilities instead of using direct PDFs or probabilities. Any questions thus far? There are other reasons as to why we use log, and we'll see them in a minute. So then I wanted to just show this widget. Now this is just a plot, and on top of that we can see some widget. So now, I think these widgets would be very helpful in this kind of a course, because you can modify certain parameters and see how things happen. And you could have also used the Streamlit app for the same. And in this case, I'm just using IPy widgets. So all you want to see is that if you vary the mu, right? So, and you vary the sigma, right? The log probability will always continue to exist. Whereas for a lot of ranges of values, the probability will just come out to be a 0 value. Okay. So one other important thing which we need to consider is that once we have a distribution, we would want to typically sample data from it, right? Can someone tell me any reason as to why we want to sample from a distribution? So one thing we discussed in the previous class also. Sorry, was there an answer? Area under the curve, or something more specific, which we saw a particular term which we heard in the last Monte Carlo estimation. So there we were using some samples from a particular distribution, either the prior or the posterior. And there are various other applications you want to do. Do you have a different answer? Okay. So therefore, various libraries provide various simple procedures, functions to get samples. So I am getting now samples, 1000 samples from this normal distribution with mean 0 and variance 1. And if I just show you the first 20 samples, they'll look something like this, right? So you'll see that there is a tendency to have numbers close to 0, but you see some dispersion. So if you were to plot a histogram, you may see something like this. Or the trouble with histograms is to be able to get a good number of bins which looks visually correct. And you can see that, so there seems to be some difference between these two kind of histograms if we see. So if you look at the top one, you may think that the density increased there and then it decreased. and then again it decreased. Whereas this one seems to be monotonically increasing and then monotonically decreasing. So instead, very often people just use kernel density estimation, which is a specific method to derive these smoothish curves. There's one interesting parameter, bandwidth adjust. So if I were to keep this to, let's say, 0.1 versus if I keep this to 5.0 versus if I just keep this to 50.0. Can you see the difference of 0.1 versus, let's say, 2.1, right? So without knowing anything much, what does bandwidth adjust do? Smoothens the signal that you're trying to consider, right? So another, when we're talking about sampling, we are generally talking about IID sampling. Now we've again looked at this term earlier, but can someone tell us what IID is? Anyone? Okay, last, Arjit. Okay, what do you mean by that? Okay, Ritik.
Independent means the value of a variable, value of one variable does not influence the value of another, probability of another variable.
Okay.
And identical means they are derived from the same distribution.
Okay, more or less correct. I would just put it in the context of what we just now did. So we call this normal.sample 1000. This is creating now 1000 IID samples. Let's see what we mean by IID. So I wanted to again create just 1000 samples from this distribution. I will write a for loop. Initially, the number of the samples is an empty list. For I in range number of samples, I create a distribution object, which is a normal distribution with mean 0 and standard deviation 1. Right? Now for each sample, right? Each sample means each time I'm going into the loop, I am using the same identical distribution, right? I'm always using the normal 0, 1 distribution across all of these samples, right? This seems like a very simple thing, but I want you to get this nicely because then it helps us understand how factorizations work and how likelihood is decomposed, right? So each time I'm drawing a sample, I'm using the exact same distribution with a mean of 0 and variance of 1. And when I'm getting a sample, I'm calling dist.sample and I'm appending it to the list of samples, right? So does my current sample, this value dist.sample is my current sample. Does it have to do anything with the previous sample or anything to do with the next sample? No. So this is meaning that our samples are independent of the previous samples or the next set of samples, right? We had two terms, IID. The first one in this case is talking about the identical distribution. The distribution is not changing over the samples. The second is the independent. The samples are independent of each other. There is no correlation amongst these samples, right? I have created these samples and I am using this plot to give a sense of whether my sampling is correct or not. Does the KD plot look correct for 0, 1 samples from 0, 1 distribution, right? And I'm now plotting these samples over time, right? Now what can you say about this kind of a plot? What does this tell you? Seems to be white noise. There seems to be, if you were to find an autocorrelation between such a series, it would be tending to 0. Right?
So instead of saying that we have 1000 IID variables,
samples from a, so we have 1000 samples from, a normal distribution. 1000 IID samples from a normal distribution.
okay. Yes.
Other questions? Okay, so while I have the solution for non-IID, so again to make something non-IID, you have two options. Make it non-identical or make it dependent. Can you think for 2-3 minutes in your notebooks and maybe try and write some pseudocode for what may be dependent sampling and what may be non-identical sampling. And then we'll have a discussion. I'll show this code as a example, and you can then see what you need to modify in this. Feel free to discuss with the neighbors. So there are two ways to think about the answer to this problem. One, you could think about starting from this piece of code and seeing what modifications you want to make. Second, you could be looking at these two plots and seeing how they'll be different if it is dependent sampling versus how it is with independent, and how it is with respect to identical and non-identical. Okay, let's go over the solution. First, I'm talking about non-identical distribution. I'm taking a very trivial example. If it is a even sample that I'm trying to generate, I'm using a normal distribution with mean 0, 2 and standard deviation 0.5. If it is an odd sample, I'm using a different distribution. The numbers are irrelevant here. The only thing you need to consider is that the distribution can change over the samples. I'm not using the exact same distribution. Right? This is a bit of a contrived example, but let's stick on to this. And the samples, are they dependent or independent now? They're still independent because you're not as such building a relationship between them. Now, if you were to see the corresponding plots, can you see that now you have, it looks like a mixture of Gaussians. So you exactly have, like you'll have two Gaussians here, right? One is the Gaussian with mean 2 and the other with mean minus 2. Right? So therefore, the PDF that you'll get, or the density that you'll get, will be something like this. And the samples also, you'll see they are zigzag, right? Because one of them is centered at 2, the other is centered at minus 2. Questions on this? So let me ask a more realistic question now after showing this contrived example. Can you tell me any real world situation where you might see a non-identical distribution, or where the identical distribution assumption will break?
Say maximum lung capacity of 2x.
Maximum?
Lung capacity.
Learn or earn?
Lung.
learning, learn, lung capacity of humans.
So here we can divide the samples into categories, one from men and one from women.
You can do that, but right, you could have done that divided into, let's say, across gender. I was looking for something simpler. I was looking for something like an intervention over time, not over gender in this case. Mean of distribution may change over time. I'm looking for something realistic. So go beyond your maths and go into more real world things. Inflation across time. Okay. Okay, inflation across time. You'd expect the inflation to be, so you'd say that the inflation is generally every year is a normal distribution with mean 4 and standard deviation 0.1, whatever. But suddenly some economic policy changes or there is global warming, something happens and the inflation rates change. Right? So that could be one thing, yes.
Distribution of temperature over a day, and when we look it over the year, then the each
Okay. So the distribution over temperature was, or the min minus max temperature was generally fairly stable before the industrial age, and now it's very erratic. We'll have a lot of climate change related things. Another thing could be, let's say the average age of a human being across the world was, let's say, a mean of 70 with a standard deviation of 10, but post COVID that has become, let's say, 60 with a standard deviation of 5. Something has changed, right? So the underlying model's distribution itself has changed. So that is an example of where identical distribution is not a very good thing to do. This sometimes happens in practice. You have deployed a model, but you see that the sales figures are very bad because the distribution has changed over time. So let's say that if we had, which company came first in India, Amazon or Flipkart? Does anyone know? Flipkart. I'm assuming that's the case. So Flipkart was making certain projections on how much sales that they'll have based on certain things. But as soon as Amazon hits the market, the distribution will completely change. The dynamics of the market will change. So that is a proper intervention, and they need to account for that intervention, which means that they'll need to see what distribution to now change. It's a distribution shift which has happened. So this was an example of non-IAD sampling, where if we had different distributions or the different samples are not coming from the same distribution. Okay, what about dependent sampling? Anyone on this side wants to take a guess? I see 3 hands on this side. No, this side. Okay, Vipul.
So the probability of drawing the second sample is just dependent on the first.
Okay. Yeah, I'll show a simpler example now. I'll say that we started off with the first sample, which was 10, right? And then I take my normal distribution to be dependent with the mean of the normal distribution is the previous sample, right? And then I get a sample from it, and my next sample will of course now depend on the previous sample in a loop. If we were to see the evolution of samples over time, does this make sense? Right, so let's start with the first sample. It was 10. The second sample will be from a normal distribution with mean 10 and variance 1, right? Let's say that comes out to be, it's increasing in this case, it comes out to be 10.5. My third sample would be coming from a normal distribution with mean 10.5 and standard deviation 1, so on and so forth, right? If I were to choose a different random seed, you may see that the behavior is very different, right? It's now showing the scale of 0 to minus 20 with another random seed 0 to minus 40, right? So the samples, if you see, they clearly seem to be very correlated to the previous sample, which is by definition of the dependent sampling that we have shown. So what you're currently seeing is also known as a Markov chain, right? It is also known as random walk. Again, two seemingly sophisticated terms, but if you were to write the code for it, it's just 2 lines of code. Right? Any questions on IID versus non-IID? Yes.
Is the word sample equivalent to random variable in this case?
I don't know what you'll. So x is a random variable. Let's say x is trying to denote the age of a person, capital X, because random variables you denote with capital. Capital X is a random variable denoting the age of a person, and xi is a sample from that random variable.
So if we say that samples are non-identical, which means they are derived from different distributions, so they are not from the same random variable.
They are so.
So why are we grouping them together?
So saying that x. So this is now data, right? Firstly, we're talking about the data, right? We don't know the inherent generating process, right? So you start from the data. We assume that the data is coming from a distribution, which is a same distribution, right? Inherently, that may not always be the case because it's a limiting assumption, right? The natural process which is creating the data may not have identity. It may not be using the identical distributions.
This is also non-identical.
This is also non-identical in the sense that the distribution is changing. It is dependent upon the previous sample. Yes. So you're getting both together. But this was just to show what IID is, and we'll be mostly sticking to IID for the remainder of this course. Yes.
So like the previous question. So the new probability distribution that is being plotted over here,
Mhm.
that can be seen as a single probability distribution, because then can we say that it has been like as a consequence, like in the posterior, can we say that okay, this has been sampled from this probability distribution, even though it is not identical?
I am not fully getting the question.
So the thing is,
So let me first again show. Here, I think it would be easier if you just wrote dist of I. You have a dist array, distributions array, and you have dist of I. For IID, across all the I, the same distribution object is being used. For non-identically distributed data, we can have different distributions.
it's like piecewise continuous function.
I wouldn't get into all those sophisticated terminologies. So just consider that the data that we are assuming for this particular class or lecture is coming from an IID distribution, but we could have also had other kinds of samples which don't come from IID settings. In one case, the distribution itself is changing over time. In the other case, the samples are correlated. Right? So that's the main assumption, understanding that I'd like you to take ahead. Further questions?
Yeah, so here you are calling it as a dependent sample. So can we say it as a dependent and non-identical because it is proven?
I don't know the specific of whether we'll call it non-identical or not, or identical or not. So because the distribution itself is changing. Yes. So I would just call it dependent as well as non-identical as for me. Yeah, but I would just to simply say I would call it non-IID. Right? But the sampling is dependent, and because the distribution is changing, it's non-identical. But I don't know if there is any specific nuances to this. Right. Yes.
So while it is sampling, it depends on the previous distribution, right?
It depends on the previous sample.
Sample. So if somehow it got into the same sampling area at some stages, will it be in a cycle?
No, it won't be in a. So the question is that if my next sample is the same as the previous sample, will we get into a cycle? Not for this distribution because it has a variance of 1, and you're trying to get a sample from a normal distribution. Or basically, this question boils down to if I have a normal distribution with mean 0 and standard deviation 1, will I get samples of 0, 0, 0, 0, 0, 0? No. Right. So So I understand where your question is coming in from, but I will not disturb the class with that question because you're getting into finite state machines and you're talking about transition probabilities without maybe knowing the specifics, but we don't need to know about that now. Okay, I think we should go ahead because otherwise we'll miss the main point. It's a simplifying assumption. It makes maths easy, it makes life easy. And it will hold in many situations. So imagine if you had to, so there are in fact questions where you don't make such assumptions. So I can in fact show a good example of that. Bayesian methods for, so if we look at Bayesian methods for hackers, it's a very good book. It starts with this example. You're talking about the number of text messages a person receives, and you're saying that at some particular day, the distribution changes. Right? So here you're trying to say that I'm trying to model the number of text messages. Now the number of text messages is what kind of a quantity? Floating point or integer? Integer. Can it be negative? No. So can you say it is a count data? What kind of a distribution do you think makes sense for modeling count data? Poisson, right? Poisson distribution. So you're trying to model this with a Poisson distribution. What you're saying is that Poisson distribution has one thing known as the rate, right, which is the most common or the expected value of the distribution. So in this case, that rate is, let's say, 18, and after a certain date, the rate is 22, right? So here, this is a case of, let me see if I can open this. So what you're saying is that the count of the number of text messages you receive for a particular day I is given as Poisson with a certain value lambda, which is known as the rate. And you're saying that that lambda is lambda 1 if time is less than tau and lambda 2 if it is greater than tau, right? So now in this case, you only have two things or three things which you're trying to now find out: tau, lambda 1, lambda 2, right? You have now broken the IID assumption, right? But you've made another assumption. What is that? The IID assumption would have said that I have a constant rate irrespective of the day in my data set. So I would use a constant lambda for all the data. I have made some more realistic assumptions, but I still have some assumptions. So I've said that I will say that the change happened at a date tau, and before tau at lambda 1, after tau at lambda 2. So you've considered some more assumptions. What if the number of changes was not 2 but 3? Right? What if instead of 3 it was more? Right? Now you're trying to make the problem much more realistic but much, much more sophisticated. What if in fact you had a distribution on the number of splits, number of times the rates changed, right? You could make all those assumptions, you could solve it using the Bayesian framework, but it gets very, very sophisticated at that point. Or you could just make a simplifying assumption and see where it gets you. Okay, so we should probably go ahead now in the interest of time. So we've looked at various kinds of sampling. One of the question in your assignment is to look into different distributions. So I'm again showing Laplace normal student t distribution. I just wanted to maybe just show the PDF. The remaining code you can borrow from the notebook. You can see the Laplace distribution seems to have a lot more mass, lot more density towards closer to 0, whereas other distributions have slightly more fatter tails. Right? So you can observe this in detail at your own time. So at this point of time, as a consequence of as a consequence of the IID sampling, what we can say is that probability of observing certain data D given certain model parameters theta, which is x, let's say my data is just some observations from Gaussian distribution, right? So let's say that these are the 1000 samples which I was generating from the Gaussian distribution, right? I have 1000 samples x1 through xn samples from the Gaussian distribution. What is theta in the previous example? The model parameters corresponding to the distribution I was talking about, so mu and sigma, right? So I'm trying to figure out what is the probability of observing those 1000 samples from a normal distribution which has two parameters, mu and sigma. So theta is mu and sigma, and I'm writing this as probability of the first sample, of observing the first sample given mu and sigma multiplied by probability of second sample mu and sigma, so on and so forth. Can you see why we are able to write this as a consequence of IID sampling? Right? The samples are all independent of each other, and where is the identical assumption coming in? All of them are using the same theta. Right? So this is a significantly easier problem to solve than if we had certain dependencies. Right? So then we'll not have factors like p of x1 given theta. We may have factors of p of x1 comma x2 given theta. Right? So those dependencies are very, very hard to create. And we can also very nicely, conveniently draw this as a graphical model. We have n observations. N was 1000 in the previous case. All of these observations depend on mu and sigma through the normal distribution object that I've created. Right? x1 is a draw from normal distribution with mu and sigma. x2 is a draw from normal distribution mu and sigma, xn is a draw from normal distribution with mu and sigma, and there is no relationship between those. So this plate like object that we see, this is used to denote independencies or repetitions as well as repetitions. Sorry, it's better to say they're trying to encode repetitions, right? x1, x2, so this is, you could have expanded x1, x2, x3, x4, x5, all of them are linked to this normal distribution through this mu and sigma. Questions? Okay. So time for some quiz now. We have 3 courses, C1, C2, C3, and no student will take more than one course. So each of the student will be enrolled only in C1 or C2 or C3. And the scores of the students in these courses are normally distributed. For some reason, the instructors thought that this is a good idea to fit a normal distribution to the marks. C1, C2, C3, 80, 10, 70, 10, 95. Right? Which course will you want to take? Third one? Okay. Are you sure on that? Could you be missing something? Sorry? Do you care about the marks or the grades? So would you be missing the relationship between grades and marks? Yes? Sorry, if the grading is?
If the grading is negative, then I get C2.
Okay. Yeah, that's the other way to think, right? So it depends on where you would want to think. You may think that probably C2 is the best course to take because the average score seems to be low, but I'm a very smart person. I'll be able to beat the other students. Or the other way to think might be that the other course will fetch me more marks, and you're also missing out a lot of variables. But that was not the question. That was just to ensure that we can all wake up after the lunch. So if we ask this question, I randomly pick up a student from one of these courses. I'm not telling you which course, but they tell me that they got 82 marks. And for keeping things simple, we assume that all 3 courses have an equal number of students. So I'm removing some of the Bayesian computation that you will have to do. So which course is this student from? So I've asked a different question than what is on the slide. Which course is this student from? Okay, Utkarsh. Let me repeat. Which course is this student from? There's a difference between which course is the student most likely from versus which course is the student from. We don't know, but it seems to be most likely from C1, right? Why? Closest to closest to the mean, right? So we, without even looking into any of the probability maths, we are able to figure out the answer quite simply. Now let's see. I've plotted the probability density function for the three courses, C1, C2, C3. C3 seems to have very low standard deviation, so most of the students are getting marks between this range. And I have C2 and C3, right? I said that I want to check the most probable class for a student who got 82 marks. So I'll pick up the x-axis, I'll draw a vertical line corresponding to 82 marks, and I look at where it intersects the three different probability density functions, right? It intersects the C2 one, which had 70-10 distribution at the lowest height, and it intersects the C1 class at the highest height, right? So based on this, what do you infer? The student is most likely from class C1 because the density is highest at C1, or the likelihood of observing 82 marks from class C1, which corresponds to mu 80 and standard deviation 10, is the highest, right? Let me repeat that. Probability of getting an 82 marker from class C1 is highest amongst the three classes because the values in this graph seems to be the highest that you get. Right? So therefore, most likely this person is from class C1, but there is a lot of probability it could be from the other classes also, non-negligible probability. It could have been from some other class also. Right? Question on this? Questions on this? Okay. So let's quickly look at a notebook for creating this. So I have again defined the three distributions corresponding to the three classes, 80-10, 70-10, 95. And that's one thing I'll encourage in this course, that you try and write simple sample codes for illustrative problems, educational problems. You'll start seeing concepts much better. So I've now taken a linspace from 0 to 105 and 1000 such points. I'm plotting the log probability. I'm plotting the PDFs for each of these, right, on this range of 0 to 105, and that gave me this particular figure, right? So we've seen this figure previously also. The only new thing which I did here, just to make it visually easier, is to draw a vertical line at 82 and then correspondingly figure out where the heights are intersecting, right? So this way we've got the probabilities. Let's go back and look at the next question. So let us now assume that this is now independent of the previous problem, right? This is a different problem. I just tell you that we have observed a value 20. You don't need to know about the units. And I'm telling you that it is coming from a normal distribution, and we know it's sigma. Sigma is 1. Right? What do you think is the most likely value of mu, which is consistent with the data that we have? Why not 19?
Because that is what we have. It's prior.
Okay. Any other answers?
Probability of mu is highest.
Probability of mu is highest. What is probability of mu?
PDF will see it will be highest.
Okay. Again, what we wanted was the likely value of mu, or we want to choose that value of mu which is most consistent with the data, or we want to maximize the probability of observing 20 from a normal distribution whose mean is mu and the standard deviation is 1, right? So I want you to, whenever we are talking about such problems, to think about the conditioning. You want to maximize the probability P of D equal to 20, x equal to 20, given that it is coming from a normal distribution with parameters mu and standard deviation sigma equal to 1. It will turn out to be 20. And in order to do that, we'll want to be evaluating the probability density at 20, right, at the data point for different values of mu, right. So, if I write this f of x equal to 20 given mu sigma equal to 1, what is this expression a function of? X, mu or sigma? Sigma is fixed. Like for now, let's assume sigma to be fixed. This is a function of mu, right? I think I want people to get clarity on this, because generally when we think about PDFs, we think about the input variable x, right? Here, this particular quantity which we are trying to maximize is a function of mu. We are trying to find out a mu which maximizes this probability. And we can then go to the notebook and try and visualize this. Our observation is 20, sigma is 1, I get the different mu's. I consider all the possible mu's which could have given me, which let's say that the feasibility set of mu's is between 0 and 40, and I've taken 1000 points for that. Now importantly, I'm plotting the line between mu's, and I'm putting a normal distribution with mu and sigma, right, and I'm evaluating the probability or the PDF of observing this value 20, right, not the other way around. We need to be very careful with that. If I do this, right, so what do you observe? Is this a normal distribution is this a normal distributions PDF that I'm plotting? Technically, no. I'm plotting the likelihood, right? I'm plotting the probability of observing 20 given mu. So, x-axis is mu, and I'm plotting that. It will come out to be the same in this trivial example just because of the symmetric nature of the normal 1D normal distribution. But this is the likelihood, right? This is the probability of observing. I think another way to look at this would be perhaps looking at this. So, I have fixed 20, same as previous example, the course example. I fixed 20, which is my observation. I am varying mu, but the likelihood is 0. What is going on? So, at mu equal to 14.9, right, the likelihood of observing 20 is 0. Sigma is very small, but 0. Numerical underflow or limitation of floating point numbers. But at least first let's see if the implementation seems to be giving us some reasonable numbers, right. At x equal to 20.3, I draw the vertical line going up, and I see where it intersects this distribution, and it intersects at a height of 0.3814. At 20.0, it intersects at 0.3989, which seems to be the maximum in this case, right. Whereas if we keep going now further away, the likelihood keeps dropping, right. So, what we saw here and what we see here are different things, right. So, what we see here is the height or the likelihood that I am getting from this plot as I am varying mu. This is a common cause of confusion. People think that the normal distribution and the likelihood are the same thing, right. In this case, because of symmetricity, you will get similar things. But importantly, you have to always, I would always encourage thinking in terms of this plot. You vary mu and you look at the height of the corresponding to the data point, which explains the data. But importantly, as I said, that likelihood is a limiting term because it involves PDFs. Right, probability density functions, which are going to suffer from underflow like problems. So, therefore, we are also plotting the log likelihood, right. Now, let us first take it to 20 and see what we get. Okay. So, based on these two plots, the above and the below one, can you actually confirm the fact that the log transform is a monotonically consistent transform? So, values which are higher here will be higher on the bottom plot also, right. So, if I move from high to low, so let us say if I move in this direction, I will also move downwards in the log likelihood plot, right. But the good thing is that for very low, very far away values of mu also, where the likelihood seems to be 0, the log likelihood is still a feasible number to compute. Questions on this? Okay. So let's now go back to our classroom example. Now we still have the 3 courses, but now we have 2 students I've picked up. Again, both of the students have been picked up from the same class, right. That's a simplifying assumption. The first student says they got an 82, the second student says they got a 72. Now tell me which class they belong to. Most likely C1 most likely, but let's see how we'd go about solving that. So thus far we've been looking at a very simple use case where we had only a single data point, single observation. Now in this case we have 2 observations. So let me show this. I have plotted the PDF for class 1 C1 and I have marked the 2 observations 72 and 82. I look at where it cuts the PDF, right. So I'll have to get 2 cuts. The probability of getting an 82 for class 1 is 0.0391 and probability of getting a 72 for this class is 0.0290. I get 2 numbers, 2 distinct probability numbers. I'll do the same thing for class 2 and I get numbers for getting 82 is 0.0194 and for getting 72 is 0.0391. So if we look at getting probability of getting 72, that is much more for class 2 compared to class 1. So compare this 0.0391 with 0.0290, which makes sense because the mean of class 2 is 70 whereas mean of class 1 was 80. So I can get the probability of getting 82 from class 2 and 72 from class 2, and similarly I can do that for class 3. But for class 3 these numbers are very, very small because it's the mean is very far and the standard deviation is very low. So it's very unlikely that these students were from that class. So now we've got a pair of numbers for each class, right. So essentially what I have is a table like this now, right. Getting 82 from class C1 has a probability of 0.039, getting 72 from class belonging to class C1 is this, right. So now I have a 3 cross 2 matrix, right. But the question was not to create this 3 cross 2 matrix, the question was tell me most likely class belonging to these set of 2 students. Yes, right. So now you go back and you look at the factorization which we discussed. Probability of data given theta, right, we can factorize it as x1 given theta, x2 given theta. So probability of obtaining 72 and 82 or 2 students obtaining 72 and 82 marks belonging to a particular class is the probability of getting 72 given that class multiplied by probability of 82 getting that class, right. So therefore now if you see the IID assumption is helping us, otherwise this would have been a very hard problem to solve if we didn't make this assumption. Coming back, so probability of getting a 80, student 1 getting 82, student 2 getting 72, can we say that that's just the product of the across the columns of the columns? So this is just the individual terms. One concerning thing you're already seeing is that getting a 72 from a class whose mean is 90 is a very small number. So let's just aggregate via the product and we get the probability of these 2 observations coming from class 1 is the highest, second highest C2, third highest is C3. and I could have plotted a bar plot for the same, and like it's very hard to now see the C3 term. Right? At this point, we've had only 2 observations, right? And it already seems that with 2 observations, some of the probability numbers that we are trying to compute, likelihood numbers that we are trying to compute, will suffer from an underflow, right? So because of this also, it is recommended that we start using the log transform, the log likelihood instead of the likelihood term, which is what I do. So now I'm saying that these are the 2 scores which I get. I have just changed the scale from linear to logarithmic. So this was if we were to do linear, right? But instead I look at the logarithmic scale, right? So I did the multiplications in the linear scale. In the logarithmic scale, what do I need to do? Addition, right? Which is the same as, this is my likelihood, right? Which is the product of, in this case, just the 2 x1 given theta and x2 given theta. If I were to compute log likelihood, that is log of observation of probability of observing x1 given theta plus log of probability of x2 given theta, right? So previously what we had multiplied the bars in the linear case, in the logarithmic case we need to add them up and see whichever gives us the highest value. I have now just to show the power of logarithmic scale, first let's go to the linear scale. Probability of getting 50 and 50 for class C3, it's 0, right? We can't compute those numbers with enough precision to be able to get something worthwhile showing here. For very large numbers, it does turn out to be some number, but if we just move all the way down, there is only class C2 which shows some very finite probability, and this is also going to 10 to the power minus 12. Just move to the log scale. For each of them, you will see some values. Right? You can then say that probably getting a 1 and a 0, you should not be taking this course. C2 is most likely, right? So you'll add these 2 numbers, add these 2 numbers, add these 2 numbers, and see whichever is the smallest number. Right? Questions? Okay, now let's do a bit of less interesting stuff, or the boring stuff, which requires some amount of maths and some amount of analytical solutions. We have certain data from normal distribution, which we've been doing thus far. We want to figure out the most likely set of mu and sigma which could have generated that data, right? So given the data, we want to choose the mu and sigma which is most likely to have generated that data, or which is just theta MLE. We're only considering the data, we're not considering the prior. So therefore, we are looking at the MLE solution. We need to know the PDF of normal distribution, which is this 1 over root 2 pi sigma square e to the power minus x minus mu whole square over 2 sigma square. We have a data set D. In this case, just assume it's some samples which we have seen at the start of the class. We took about 1,000 samples. Each of the sample is independent, coming from the same distribution, and we want to estimate the parameters theta equal to mu and sigma from the data, right? So before this, can someone tell me the difference between what you understand by population and sample? You might have studied this in some economic course or something, some other branch. Right. So the sample is generally considered to be a subset of the population. So even in terms of what happens at exit polls, right? So different news channel come up with different estimates, right? How do they do that? Do they go to each and every human being and ask whom have you voted for? That is not allowed and that's not feasible. Right? How do? They try to get a representative sample of the population, right? And from that, they're trying to derive certain statistics, right? Same things happen when we're talking about deriving certain estimates. Now we're trying to estimate the parameters theta equal to mu comma sigma. We typically be given a sample, right? I said a sample of 1,000 points, sample of 10,000 points. The population would be all the possible values that could have been generated from that distribution. In the case of linear regression, the population might be infinite amount of data, right? But we'll never have access to that. We'll always get a finite sample of data using which we want to identify the best set of parameters which describe that data, right? So that's one important distinction between population and sample. The reason I'm discussing about this specific topic is that there are certain kinds of estimators where you have to be careful about sample and population, right? And the kind of estimators value that you get, they can have certain amount of bias. Right? This is the hint. I'm not going to be able to cover that in today's class. We can start off with the likelihood function, right? Now we're saying that can you figure out mu and sigma which would have best described this data set of n samples. We can write this as probability of data given theta, which is the likelihood function. Importantly, the likelihood function is not a function of the data. Like the data is assumed to be given to it as an auxiliary variable or constant. It's a function of mu and sigma or theta. So the function of mu and sigma, it is the PDF of xi given mu and sigma square, and then there's the product term of going from I equal to 1 to n. Why do we have this product term? Because of IID, right? We can factorize this likelihood term as the product of the individual PDFs evaluated at mu and sigma for that particular data point xi. So we can write it this way. We can also write the log likelihood function, which we have now seen that why it makes sense. If we take the logarithmic of this, the first beautiful benefit of using a log is that the products get transformed to summations, and it's easier to work with summations than to work with multiplications, especially when you're trying to compute things like gradients, right? So is it easy to compute if you have a plus, so you have a and b which are function of x, is it easier to compute del of a plus b with respect to x, or is it easier to compute of a into b? Always a plus b, right? It's an easier term. So you have log likelihood. It's summation of the log probability, log PDFs. So the log prob which torch-like objects give is this term, right? We evaluate it at each and every xi. So one main difference in the implementation and what we're writing here is the vectorization. So libraries would just implement this. You could just give, instead of xi, you could give the entire vector. You'd get another output vector which is corresponding to the log prob, and you could then take the dot sum of that, right? So if we simplify this equation, we can put this value of f of xi and do a bit of adjustment. So we'll get this log of 1 over 2 pi sigma square plus log of this, and after a bit of reduction, we'll get a term which is independent of sigma and mu, right? It is a log 2 pi minus n by 2. It depends on n, but independent of mu and sigma. You have a term which depends on sigma, and you have a term which depends on both sigma and mu, right? So in the next class, we'll see that we want to be able to maximize this function, right? Which means that with respect to a particular value mu or sigma, we want to find that mu or sigma which maximizes this. I can show you the result first. As expected, the estimated value will turn out to be just the mean of the data, right? If you consider data, normal distributed data, if you just take the mean over it, that will be a very good estimate of the mean of the underlying normal distribution. The interesting thing comes in when we are trying to compute the MLE for sigma, and it will require a little bit of more maths, but it does turn out to be just a sample variance, right? So your best estimate for variance is a sample variance, but there's a nuance to it that this is known as a biased estimate, right? This is not the best estimate that you can get. This also involves the fact that you're dealing with samples and not populations. Right? So let's consider a thought experiment. Let's assume that this entire room is the population of all the people who take the ES661 course. Right? That's the entire population. For some reason, in none of the class, all of the students are present. So I'm always dealing with a sample or a subset of the students, and I ask each of them to tell me their marks. Right? Let's say in one of the class, I only get 10 students. Right? So maybe these 10 students have ranges from 70 to 90. Right? But the entire population had ranges from 60 to 95. Right? So when you're considering whenever you're considering the sample, it's very likely that you'll not see the full range. Right? So therefore, that may introduce a bias, right, which we can mathematically also show. But intuition-wise, I think this is more important to consider. Given a sample, for the variance term, you may not be able to see the whole range. Right? Therefore, you may be underestimating the variance, right, which is causing a bias. Okay. Any questions? Next class we'll again start with the derivation, but I think it's simple enough that you can do on your own. I'll release the slides. Any questions? Okay, so we can then discuss about the class timings and